Welcome to an extraordinary exploration of the Sun, our solar system's central star. And you're watching Astronomy. Today, we're going on a journey through different wavelengths of light to unravel the mysteries of the Sun. From its enigmatic corona to the solar flares and sunspots, we will delve into the heart of our star, uncovering its secrets through the lens of advanced technology. As we gaze into the vast and awe-inspiring cosmos, we are surrounded by countless stars. However, one star reigns supreme in our skies and profoundly influences our lives: the Sun. Its intense and vibrant presence at the heart of our solar system has sparked a myriad of myths throughout history, born from its captivating brilliance. Now, with technology surpassing even the wildest dreams of our ancestors, we have the tools to delve deep into the intricate workings of this nearby yellow dwarf star. Embarking on a journey through its dynamic atmosphere, we uncover extraordinary phenomena. I am Alex McColgan, and you are tuned into Astronomy. In today's episode, we're going to immerse ourselves in the Sun, utilizing various electromagnetic wavelengths to reveal this star in an unprecedented light. In previous episodes, we've journeyed through Jupiter and its moons, examining them through the electromagnetic spectrum. If you're curious, you can check out that episode here. This time, we shift our focus from a planet to a vibrant sphere of plasma, applying a similar investigative lens to understand this energetic entity. The light from the Sun that reaches us is like a message from the past. Despite being the fastest thing in the universe, sunlight takes about 8 minutes and 20 seconds to travel from the Sun to Earth. This means that we see the Sun as it was a few minutes ago. Furthermore, the journey of photons from the Sun's core, traversing through its many layers before escaping into space, means that the light that finally graces us is aged between 10,000 to 170,000 years. To begin exploring, let's approach it like peeling an orange, starting from the outside and working inwards. Our first focus is the Sun's outer atmosphere, the corona. The image we'll examine was captured by the Solar Dynamics Observatory (SDOA-NASA) mission launched in February 2010. The SDO's goal was to enhance our understanding of how solar activity affects Earth and our technological infrastructure by studying the Sun's surface and atmosphere across different electromagnetic wavelengths. Utilizing light beyond the visible spectrum, NASA could unveil details about the Sun that are typically invisible. This particular image was captured using a 19.3 nanometer wavelength, which falls in the extreme ultraviolet region. With this wavelength, corresponding to a color temperature of about 1 million Kelvin, the higher regions of the Sun's corona are vividly visible. Fascinatingly, the Sun's corona is also sometimes visible to the naked eye during rare astronomical events. During a total solar eclipse, when the Moon aligns perfectly between Earth and the Sun, we witness a unique celestial event. The Sun's brighter disk, known as the photosphere, is completely obscured, unveiling its glowing outer layer. This sight is already mesmerizing, but the corona appears far more intricate in images like those captured by the Solar Dynamics Observatory (SDO), making them invaluable for scientific research. Delving deeper, just below the corona, we encounter features of the Sun at a staggering color temperature of 20 million Kelvin. These intensely bright spots signify solar flares, which are dramatic and awe-inspiring phenomena. Take, for example, this footage from a particularly active period of solar flares in August 2022. Solar flares are fascinating yet formidable events where the Sun ejects a massive amount of electromagnetic radiation. They occur due to the rapid crossing, distortion, and reorganization of magnetic fields, driven by the turbulent plasma within the Sun from which these fields arise. But solar flares aren't the only sources of radiation in the Sun's atmosphere. Coronal holes, shown here as darker areas on the Sun, are another significant feature. Coronal holes are another intriguing aspect of the Sun we can examine more closely with extreme ultraviolet light. These are cooler and less dense regions of plasma, characterized by their open magnetic fields. Unlike closed magnetic loops that reconnect to the sun's surface, the field lines and coronal holes extend outward into the solar system. This structure allows particles from the solar wind to escape more readily into space. When these solar winds travel towards Earth and interact with its magnetosphere, they create the spectacular auroras that illuminate the night skies near Earth's poles. Ultraviolet light provides an enhanced perspective of these captivating elements of the sun's outer layers. The use of non-visible spectrum light opens up a world of discoveries. The sun's outer layers are teeming with phenomena, including solar filaments or prominences. These are vast loops of plasma that arc from the sun's surface, adding to the complexity and beauty of our star. These massive plasma loops, known as solar prominences, dwarf the Earth, making it appear minuscule in comparison. They can stretch for hundreds of thousands of kilometers into space. While some can form in just a day, a stable prominence may linger in the corona for several months. In this particular instance, we observe a prominence emerging from the photosphere and descending into the sun's atmosphere. Even though this video is accelerated, with minutes passing like seconds, the rapid movement of the prominence, driven by the sun's powerful magnetic fields, is evident, especially considering its immense size. An intriguing aspect of the sun's atmosphere is that it experiences a form of rain. Not all the charged plasma ejected into the corona continues its journey across the solar system. Some of it gets trapped and cools in the corona, eventually falling back to the sun's surface as coronal rain. While this phenomenon is visually stunning, it's wise to admire it from afar, considering its temperature is still in the range of millions of degrees. However, this gentle return to the sun's surface isn't the destiny of all the sun's plasma. This is where analogies to Earth's weather systems fall short. Unlike Earth, where clouds have a predictable cycle, the dynamics on the sun are vastly different. On Earth, clouds don't suddenly burst, releasing energy like a snapped elastic band. But on the sun, with its intensely coiled magnetic fields, this kind of dramatic release does occur. This is showcased in a time-lapse of a coronal mass ejection. Observe how the structure gradually forms at the lower left of the sun, and then, in a sudden burst, it releases billions of tons of plasma into the solar system. Such powerful ejections pose a significant threat to our satellites and electrical grids, even with Earth's protective magnetic field. These phenomena are captured by the Solar Dynamics Observatory, SDO, using a 30 nanometer wavelength, which falls in the extreme ultraviolet range of the electromagnetic spectrum. The timing of these observations is crucial, as the frequency and intensity of such solar events vary, being more common in certain years. Each of these structures is linked to the sun's solar activity, which follows an approximately 11-year cycle, a topic I recently covered in another video. But there's still more to uncover. Just as visible and ultraviolet light reveal different aspects of the same solar features, employing various wavelengths of non-visible light can provide even more insights. To illustrate this, consider these two images of the sun's corona, each captured at different non-visible wavelengths. Captured over the same time frame, these two images use distinct wavelengths of light to unveil different aspects of the sun. The first image, taken at a color temperature of 600,000 Kelvin, reveals the quieter areas of the corona, showcasing coronal loops. The second image, captured at a much higher color temperature of 2 million Kelvin, vividly displays the corona's active regions. This stark contrast between the two images underscores the necessity of employing varied methods to explore the complexities of our star. What might seem like a single solar event at first glance can actually be a multifaceted and interconnected series of phenomena. Yet, we haven't fully traversed the sun's atmosphere. Venturing further inwards, let's examine another image from the SDO, this time using a 160 nanometer wavelength of light. This image focuses on the transition region, a thin layer situated between the sun's corona and its chromosphere, which is the lowest layer of the sun's atmosphere. The transition region, although relatively thin, is a crucial area to study. In the transition region of the Sun, which spans about 100 kilometers in thickness, the temperature undergoes a dramatic surge, escalating from approximately 8,000 Kelvin to a staggering 500,000 Kelvin. To draw an earthly parallel, consider the molten lava from Hawaii's Kilauea volcano, which reaches around 1,170 degrees Celsius or 1,443 Kelvin. The lower end of the Sun's transition region is nearly 6 times hotter than this lava, while the upper end is over 346 times hotter. Delving further, we enter the Sun's chromosphere, the final atmospheric layer before reaching the Sun's surface. Captured using 170 nanometer ultraviolet light, the chromosphere is estimated to be around 1,700 kilometers thick. Within this layer, we observe fascinating structures called spicules. These plasma jets, resembling long, swaying blades of grass, burst upwards from the Sun's surface at speeds reaching 100 kilometers per second, about 282 times faster than the speed of sound. They can extend up to nearly 10 kilometers in height, surpassing the elevation of Mount Everest. For a long time, the formation process of spicules was a mystery, especially regarding how magnetically charged particles could overcome the Sun's magnetic fields. However, in 2017, a breakthrough came when a research team incorporated neutral particles into their model. Previously, neutral particles weren't considered impactful, but their inclusion revealed that they provided the necessary buoyancy for magnetically charged particles to break free and form spicules. As we move down through the lower layers of the Sun's atmosphere, we eventually arrive at the photosphere, the Sun's surface, optimally imaged in visible light. While the edge of the photosphere seems crisp and defined, as it often appears to our naked eye, the reality is more intricate. The apparent sharpness of the Sun's edge is mainly due to its immense distance from Earth. The Sun itself is not a solid body. Given its extreme heat, matter within the Sun cannot exist in solid, liquid, or gaseous states. Instead, it exists as plasma, often considered the fourth state of matter and estimated to constitute 99.9% of all matter in the universe. Plasmas are similar to gases, but consist of a mix of ionized atoms and free electrons. The photosphere, visible in this image, is the outermost layer of the Sun, about 400 kilometers thick. It isn't a fixed, solid boundary, contrary to what the image might imply. Unfortunately, this layer is as deep as scientists can directly measure. Upon closer examination, you may notice dark spots on the left-hand side, known as sunspots. These appear darker than the rest of the photosphere due to their relatively cooler temperatures, though they are still extremely hot. Sunspots differ from coronal holes. They form in areas where magnetic fields are particularly strong, trapping heat beneath the photosphere and reducing convection within these regions. When comparing this image to another captured using extreme ultraviolet light over the same period, a link between sunspots and solar flares becomes apparent. Solar flares and sunspots often occur at the same locations, suggesting a direct relationship. Focusing now on some specific sunspots, this image was captured using the Swedish Solar Telescope, located here on Earth with a visible light wavelength of around 400 nanometers. Near and around the sunspots, the photosphere is filled with jagged-edged, constantly morphing cells, resembling cooling and cracking lava. However, these structures, about 1,000 kilometers wide, are known as solar granules. They represent the uppermost layer of a dynamic convection cell. The brighter areas within each granule signify hot fluid rising from deep within the Sun's upper interior to its surface. Once it reaches this boundary, the fluid spreads outwards and across, cooling gradually before sinking back down at the rough, dark peripheries of each cell, thereby completing the cycle. This process is akin to the convection currents in Earth's mantle, which drive plate tectonics. The dynamics here are extraordinary. On average, each granule may last only about 20 minutes, Yet the flow within these cells can reach supersonic speeds exceeding 7 kilometers per second, creating surface waves due to sonic booms. Interestingly, these granules are also visible in the full disk view we examined earlier, using the same wavelength of visible light. The apparent graininess of such a high-resolution image is not due to any image processing artifacts or noise, but rather it's the granules themselves on the sun's photosphere. Regrettably, this marks the limit of our exploration. Current technology and methods haven't yet allowed us to image deeper layers of the sun, whether using visible or non-visible light. Much of what lies beneath this photospheric layer remains a mystery. However, the use of varied light spectrums has proven invaluable in our study of the sun, enabling us to observe solar phenomena like exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and the ever-changing granules in ways that were previously impossible. The sun is a hub of incessant activity, much of which would remain hidden without these advanced imaging techniques. Perhaps in the future, we will develop methods to peer even deeper into the sun, employing techniques that are, for now, beyond our wildest imaginations, just as the ancient civilizations could hardly fathom the methods we use today to explore the cosmos. Our current understanding of the universe still leaves much to be discovered, sparking both excitement and curiosity. The unseen wonders of the universe, now within our reach thanks to modern technology, continuously fuel our quest for knowledge. Have you ever wished to witness the sun's features with your own eyes? Of course, looking directly at the sun without protection is dangerous. However, there's an upcoming opportunity to see the sun's corona without the need for telescopes during the grand total solar eclipse on April 8, 2024. For this event, proper eye protection is essential. Today's video is sponsored by Visa Solar, a supplier of NASA-approved, ISO-compliant eclipse glasses. These glasses allow you to safely view and photograph the sun's corona. Visa Solar's products, manufactured in the USA, are available individually or in family-friendly combo packs. They also offer an innovative smartphone photo solar lens for safely capturing solar images. To avoid missing out on this rare event, as the next US eclipse isn't until 2044, consider purchasing early. By using the link in the description or my QR code, you can receive a 20% discount on your purchase. Check it out and be prepared for an unforgettable solar experience. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and a sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thank you for tuning in. Interested in diving deeper into the mysteries of the sun's corona? Be sure to watch this additional video I've linked here. I extend my heartfelt gratitude to my patrons and members. Your support is invaluable. If you wish to have your name featured at the end of each Astrum video, please explore the options available through the links provided below. All the best, and I look forward to seeing you in the next episode.